Thank you very much for the introduction. And it's my greatest pleasure to have this opportunity to speak on this wonderful occasion. And for today's talk, I have brought a book with me. And I'm going to talk about it in a moment. But let me begin with the other two books, which I received from Hiroshi Oguri-san. And these two books are popular science books Oguri-san had written for years. And so J1 already mentioned this book. And I'm not going to talk about the contents of these books, except that these are fantastic reads. And I highly recommend them. Even for professional physicists, you will learn many things like Oguri-san's drawing ability, illustration things. And the only thing I wanted to add here is that the occasion I received this book from Oguri-san is at his home party at his house in Pasadena, which was, of course, previously fun with good music, good conversations, good food prepared by Kyoko-san. And I can say that Oguri-san is not only a pioneer and a role model, almost a host father for many generations of physicists who would like to study in the United States, coming from other countries, like Japan, or more broadly from Asian countries. And we are, all of us are thankful for that. And coming back to this book, so this book is in certain sense backup. This is real preprint of PCOB's paper. And well, it's more than 100 pages. It's really a book and published by Kyoto University. And here is Oguri-san's signature. We were talking about the topological string amplitudes to understand the physics of self-dual field strength, self-dual gravity photon field strength at the time. And somehow, Oguri-san came up with the idea that I should have this book. And the obvious interpretation was that I should learn topological string amplitudes more to compare the project with Oguri-san. But I thought there was more to it, because he often added that your brain functions sharpest at your age, I mean around mid-30s, and these days never come back. And my interpretation was that I should work hard at the time to write a paper as good as PCO. Everybody knows that he's very proud of this collaboration, and that's why he gave me this book. And I'm not sure whether it was successful, but it was a great encouragement. And in this talk, well, self-dual field strength will appear as our main ingredient in a little bit twisted way. So to explain this, let me set up our stage. So the main theme I want to discuss today is a distinction between scale invariance and conformal invariance. And as we know, that conformal invariance plays a very important role in our understanding of theoretical physics, starting from the two-dimensional worldsheet description of the string theory, ADS-CFT obviously, as well as the recent developments of numerical conformal bootstrap to understand critical phenomena. But in many situations, we only assume scale invariance. But somehow, conformal symmetry or conformal invariance seems to emerge. But in this definition, there is a gap between the assumptions of the conformal assumption of scale invariance alone and the conformal invariance, because conformal invariance means that we have an extra symmetry associated with the special conformal transformation that is not encoded, not assumed in the assumption of the scale invariance alone. But in many examples that we know, somehow we have the conformal invariance. And the question was why? Well, let me formulate this question in terms of the properties of the energy momentum tensor of a quantum field theory. And we are mainly interested in a local relativistic or Poincare invariant, or after the Rikkyo rotation, Euclidean statistical QFT, which automatically has energy moment tensor that is conserved and symmetric. If your theory is invariant under the scaling transformation, then the trace of the energy momentum tensor has an extra property, such that it is given by a divergence of a certain vector operator J mu, which is sometimes called the biliary current. And if this equation holds, then you can construct a conserved dilatation current like this. And your theory is scale invariant. If your theory has an extra symmetry corresponding to the special conformal transformation, then there is a further constraint, further conditions on this biliary current, such that it is given by a gradient of a scale operator. And if this is the case, then you can improve the energy momentum tensor so that it is traceless. And as everybody knows that if you have a traceless energy momentum tensor, your theory is conformal invariant. But if you only assume scale invariance, it is not obvious whether your theory is conformal invariant. In other words, if the biliary current in your theory has a structure such that it is given by a gradient of another operator. And let me show you one example here. And this example is very simple, but it is kind of interesting. So let me consider a free U1 case theory in arbitrary d dimensions. And the action is like this. So this is a generalization of the Maxwell theories in higher dimensions or lower dimensions. And the theory is massless and non-interacting. So the theory is obviously scale invariant. However, it turns out that this theory is not conformal invariant. And there are various ways to see it. You can compute the three-point functions of these invariant operators, or you can just compute the trace of the energy momentum tensor like this. And unless you're in 4 dimensions, and this will not vanish, well, I said that this theory is scale invariant. So you can rewrite this trace of the energy momentum tensor in a different way like this by using the equation of motions. And then you see that, now the trace of the energy momentum tensor is given by divergence of the biliary current. But this is the end of the story. There is no way to rewrite this expression further into a gradient of a scalar operator. So this theory is not conforming. On the other hand, if you look at many examples that you know, you typically assume that if you have a fixed point of the beta functions, you claim or you just state that your theory is conformal invariant. To understand this gap, there are several attempts to argue for the enhancement or the emergence of symmetry from the scale symmetry. And there are 2 main arguments, and one is based on the unitarity, and the other is based on the genericity. And in this talk, I eventually going to focus on the second argument based on the genericity. But let me say a few words about the argument based on the unitarity, because it has some more rigorous foundations. So we know that in 2 dimensions, and there is a work by Zamolodchikov and Polchinski that states that in 2-dimensional unitary scale-invariant quantum field theories, you automatically get conformal invariance under some technical assumptions. And the argument is based on the C theorem. Over the last decades, people have been working on how to generalize this kind of idea in higher dimensions, in particular in 4 dimensions. And there is a lot of work, including the one by Shubinma, Konagotsky, Rikkyo, Polchinski, that tries to generalize this idea in 4 dimensions. Again, the key idea is that monotonically decreasing A functions. And I'm not going to tell you the details of the argument, but I'm just showing you main idea. The idea is that suppose your theory is scale invariant, but not conformal invariant. And still you can compute how the central charge A decreases there. And it turns out that in unitary theories, even if your theory is scale invariant, A seems to decrease forever. Since A is bounded, this should look like contradiction. And in order to avoid this contradiction, they argued that in certain correlation functions that contribute to A, the trace of the energy momentum tensor must be on shell 0. And this looks like you can improve your energy momentum tensor so that it will be traceless, therefore your theory will become conformal invariant. Now, this argument is nice, but it only works in unitary theories. So if you don't have unitarity, like if you are working on the statistical field theories without reflection positivity, then you cannot use this argument. Also, in this argument, we cannot have a similar argument in odd dimensions, like in 3 dimensions or 5 dimensions. So given this situation, people come up with the other idea that we're not going to talk about every theories, but we are going to work on generic interacting field theories. And the genericity argument goes like this. Again, if you assume your theory is scale invariant, then the trace of the energy momentum tensor is given by a divergence of the linear current operator like this. But we know that the scaling dimensions of the energy momentum tensor is exactly d. And then this equation tells you that the scaling dimensions of this linear current operator must be exactly d minus 1. But this linear current should not be conserved. Otherwise, it will be 0, so it will not contribute to the trace of the energy momentum tensor. So this genuine is likely a random vector operator, which is not the concern. But if you consider generic interacting quantum field theories, this kind of operator looks like get renormalization. Or in other words, it would be like to get some anomalous dimensions. So the situation that this has exactly d minus 1 scaling dimension seems to be very fine-tuned and unlikely in generic theories. That is the basis of this genericity argument. And that's why, according to this argument, that's why you almost always get conformal field theories rather than scale-invariant field theories as a fixed point. I'm not sure whether this type of argument is very convincing. And that's why I would like to come up with several theories, several infinitely many examples of theories of scale invariance without conformal invariance to see whether this genericity argument really holds or not. And the key to construct such series of theory is to use the idea of the topological twist. There's a twist. And to do this, let me just explain what is twist. So we are considering the d-dimensional quantum field theory, or CFT, for this purpose, with particular global internal symmetry, which is given by OD. It is crucial that this d is same as space-time dimension d. Now, if your internal symmetry is OD, then you can define a new rotation or twisted Euclidean rotation by considering the diagonal of OD, space-time OD, times OD of the global symmetry. And you declare that this diagonal of OD is the rotation symmetry of your theory. And under this twist, the Lorentz spin and the internal spins are mixed. For example, suppose we have the original vector operator in the original theory with extra vector internal index I. So mu is the space-time index, I is the internal index. But now, after the twist, then I to be identified with the space-time index mu, then this becomes a rank 2 tensor or rank 0 scalar. And if you do this kind of twist, then unitarity or reflection positivities are typically lost. For example, I mean, in the topological twist, in the context of topological twist, people often say that the spin statistics are broken. But the reason why people would like to do this is to get a scalar superpositivity, for example. So general quantum invariant field theories, supercharges are spinor. But if you combine the internal symmetry with the space-time symmetry, space-time rotation, then you can construct a scalar supercharges. And you can use this scalar supercharge for the BRC operator and to get the cohomology, and then you get the topological field theories. That's one way to use the twist. And such an idea is known as a topological twist. Okay, so there is a relation with this topological twist in the conformal symmetry in relation to scaling transformation. Well, if you do this kind of twist in the language of the Lagrangian, what we do is to add extra coupling between the spin connection and the internal current. So J mu is a rotation current that we'd like to use to get the twist. And here, omega is a spin connection. Usually, there is no coupling between this operator and that operator. But now, since you're identifying the Lorentz index with the internal symmetry index, there is a possibility to allow this coupling between omega and J. Actually, this coupling can be found in this Lewis paper in 2 dimensions. But now I'm talking about the situations in higher dimension. Since omega spin connection depends on the field line or metric, the energy momentum tensor is an extra contribution from this current, and the computation gives you this fact. And now, in order to see whether this theory has a conformal invariance, you can compute the trace of the energy momentum tensor, and the new trace of the energy momentum tensor is given by the trace of the original energy momentum tensor, which is assumed to be 0. So there is a further contribution from here, and this you are in 2 dimensions. In 2 dimensions, as can be seen from this paper, there is no contributions to the trace of the energy momentum tensor. The other off-diagonal component of the trace, the energy momentum tensor, T plus plus or T minus minus, will get a contribution, but there is no contribution to the trace. So conformal invariance is not broken by the topological twist in 2 dimensions, but if we do this in high dimensions, then the trace of the energy momentum tensor is modified, and there is a contribution from the OD currents you used to twist your theory. And this was already written in a classic paper by Rikkyo to do this kind of topological twist in 4 dimensions. Well, of course, topological twist doesn't do anything if you are working in the flat space-time. It is just a renaming to your theory or fields in your theory. So in a certain sense, the special conformal symmetries after the twist is hidden and there. And also, I should say that even if you're working in a curved space-time, if you take the BRC cohomology in a topological twisted setup with respect to the scale of supercharge, then the energy momentum tensor, the new twisted energy momentum tensor is BRC trivial, so the theory becomes topological. However, in this talk, I would like to not take the BRC cohomology, and further, I would like to deform the theory so that this extra piece will remain. So what is the strategy? What I would like to do is to deform this topologically twisted theory by a topologically twisted scalar. So after the topological twist, you have many additional scalar operators than you had in your original theory. Example, suppose your theory originally had a vector operator with internal index I. This operator, you cannot use this operator to deform your theory in the original theory because that would break the Lorentz invariance or Euclidean rotational invariance. But after the twist, then this contains a scalar, twisted scalar, and then you can use it to deform your theory. And a similar thing can be done with other higher rank tensors like this. So now, my idea is to add these twisted scalar operators in your topologically twisted theories and study the renormalization group flow. And my claim here is that in many situations, you would find a non-trivial fixed points generated by studying the RZ flow induced by these topologically twisted scalar operators. And they would become, in most cases, scale-invariant, but not conformal fixed points. At least the RZ flow is perturbative. The argument is very simple. So perturbatively, adding this operator will change the trace of the energy momentum tensor a little bit. That is suppressed by the coupling constant, induced by the beta function corresponding to this twisted scalar deformations. But there is already an order 1 violation of the trace of the energy momentum tensor by the billiard current due to the topological twist. So this term cannot cancel this term, at least perturbatively. Well, what's the point? Point is that after these deformations, you are not able to undo your topological twist because now you're deforming your theory by this operator. So you are not preserving original Euclidean rotation as well as the internal symmetry of OD, but you are only preserving the diagonal of OD. So there's no way to undo the twist. So there is no way to remove this biliary current operator from the trace of the energy momentum tensor in this setup. So what I say is that if you construct a theory in this way, you almost always, suppose there is a RZ fixed point, you almost always would get scale invariant field theories without conformal invariance. This looks quite general, but it seems likely that it would violate the argument I gave you earlier about the genericity. So I'm interested in this, in particular, I'd like to compute what happens. I'd like to know what happens to the genericity argument. And for this purpose, I'm going to tell you 2 examples. One is from a field theory example, and the other is from the holography. So let me begin with the QFT construction. And according to my recipe, I start with OD symmetric field theories in D dimensions, and the simplest of which is just a free massless scalar, the components free massless scalar like this. And now I would like to do the topological twist by identifying this I index, internal index, with the space-time index mu. And what you get is just a free massless vector field. And it is similar to the vector theories, box-rank theories in Feynman gauge, this. And now you deform the theory by introducing interactions to have a non-trivial fixed point. And let me begin with a not a twisted deformation, but a usual scalar deformations like this. So this deformation originally existed, and now I'm just deforming the theory by this deformation. And what you get is, well, you would get a non-trivial fixed point, and at least when D is close to 4. But this is just a Wilson-Fisher fixed point. And this, since this interaction preserves this OD of the original Euclidean rotation, as well as OD of this internal symmetry then this is just a renaming of your theory. And what you get is the same theory as before, and the twist can be undone. So there is nothing new. The Fisher fixed point, the conformal fixed point. Let me reform this theory with a twisted scalar operators. So this is the original setup, and then I introduce this interaction to make it interacting. But now I'm going to add this term. So this is the twisted scalar deformations because this index on this phi field was originally I index, and in the original theory there is no way to construct I index with mu index. Now after the twist, there is a way to construct these indices, and now you have these extra deformations.
So I understand that this is a non-unitary theory.
No, it's
In
non-unitary.
the sense that if you rotate back to Lorentzian signature space, you have phi zero component in some sense.
Yes,
Negative.
space of the course.
Yeah.
But what I wanted to do is the staticity argument.
Yes, I understand your motivation. Yes.
And reason I'm going to tell you, I'm going to tell you the the realization of such systems in nature. But anyways, it's not really good. And I want to understand whether this has a scale invariant without conformal invariant fixed point, as I promised earlier. And this theory was actually studied long time ago for knowing whether they are scale invariant or conformal invariant by Aharony and Fisher. This Fisher is Michael Fisher, so they have their motivation to study this system. And then they did the quantitative computations by doing the epsilon expansions. So if the dimension D is 4 minus epsilon, then you can find the quantitative fixed point.
Is it Aharony the father of O4?
I don't think so.
They are not related.
So sure. Different Aharony.
The answer is yes.
Yeah, really?
Yeah.
Oh, I didn't know that. Oh, thank you very much.
Yeah, that's what I thought. Yeah.
Oh, I think I was talking with Rikkyo, and that this Aharony is not a open Aharony, but
Yeah, that's clear. That's obvious.
Okay. Now, so they did an analysis, and then they found that there is a fixed point, non-zero lambda, that Z is at infinity. So in certain sense, if you look at it as a gauge theory, then this looks like a lambda gauge fixed point. Your vector field is transverse, and then there is a non-trivial fixed point there. And then the theory becomes interacting scale invariant, but not conformal invariant. And with the reasons I gave you earlier, and you can compute with some correlation functions and see, and this is, you can clearly see that the theory is not conformal invariant. And what I showed with Rikkyo is that this theory is very interesting because although the theory is interacting, and the linear current is actually not renormalized, and there is no the dimension of this linear current operator is exactly d minus 1, and this is consistent with the equality of the mu is given by divergence of the linear current, but it violates the argument of the genericity. So this is an interesting example. Let me tell you one interesting interpretation of the result. So this tells you how to understand the topological twist in nature. So people often say that topological twist is a mathematical trick to get a good theories. But in this particular example, topological twist is realized in nature. So to compare what is happening, let me begin with the usual magnet. So I'm studying the three-dimensional case, and suppose you have a three-dimensional magnet, you usually describe it as an O3 invariant under Ginsburg theories like this. And the point is that this I index was originally a vector in space-time. It is a magnetization vector. It is a space-time vector. However, in non-relativistic systems, that we know is that there is a separation of spin and orbit. So it is possible in the non-relativistic limit to regard this space-time index of the magnetization vector as an internal rotation. And that's why we have the O3 invariant under Ginsburg theories like this. But what I said can be validated by a relativistic effects. We know that in relativity, there is a coupling between the spin, rotation, and orbital angular momentum. And indeed, these people, Aharony-Fisher, found or argued that there is a dipolar interactions in real relativistic magnets that would break the spin-orbit separation. And they construct this kind of non-local interactions, and effect of which can be mimicked by the interaction I introduced here. And so, even in the actual magnet, if you consider heavy metal, then there may be, we may have to introduce this topological twist, and then this index I should be identified with the space-time index, and then you have to allow the twisted scalar deformations. That is the interpretation of the topological twist, or just twist, in the real material. Indeed, people got interested in a certain heavy metals or heavy ferromagnet, and this is a material called europium oxide. And these people found that this europium oxide shows the Aharony-Fisher fixed point rather than the Heisenberg magnet, Heisenberg fixed point. So, this is the europium oxide. This looks like a white powder, but this is curious because usually if you have a magnet, you expect it to be a metal, but here it is just a powder, a white powder. It is oxide, europium oxide. So this material, people got interested in this material because it is a ferromagnet, but semiconductor as well. So in this material, topological twist is realized, and then this scale invariance without conformal invariance is seems to appear. Now, let me show you another example from the ADS-CFT for holography. We work on ADS-4 cross CFT3 correspondence. And in the next slide, I'm going to show you the M-theory uplift of my solution. But let me begin with the effective field theory, given by the Einstein theory coupled with SO3 or SU3 Mills fields like this. Now, my idea was that, well, this theory obviously a ADS-4 background. I would like to deform this ADS-4 background by a twisted scalar operators to find a new fixed point that could correspond to the scale invariance without conformal invariance. And my ansatz is like this. So you have the usual Poincare foliation of the ADS space with extra warp factor. And I also introduced the SU2 gauge field or SO3 gauge field with this ansatz. And this ansatz was chosen so that you only preserve the diagonal of the space rotation and the internal rotation that acts on the SO3 gauge field like this. And if you substitute these ansatz into this equation motion, and you can find a very elegant scaling solution like this. So this solution has constant warp factor. So the geometry itself is ADS. It looks like conformal invariant. However, the matter, the SO3 gauge field, has this property so that it only preserves the rigid scalar transformation. It does not preserve the special conformal transformation. It does not preserve the original rotation, but it does preserve the twisted rotation. So the geometry itself is ADS, but the matter seems to break the full isometry of the ADS down to the scale transformation and Poincare transformations. We typically do not expect such a behavior in the Lorentzian signature field of studies, because if there is anything happening in space-time in the Lorentzian signature, then you'd expect that will induce some energies, non-energy, for instance. And then that would back react to the geometry so that the isometry of the space-time would be lost. However, this was possible in a Euclidean signature because this ansatz gives you a self-dual field strength. And what is special about the self-dual field strength is that corresponding energy momentum tensor is always zero. So it would not back react to the geometry, but we can break space-time symmetry by the matter sector. And this is the very elegant use of the self-dual field strength to generate scale invariance without conformal invariance in the Euclidean signature. You cannot expect to do it in the Lorentzian signature. And that's why I focus on the Euclidean signature ADS CFT. And you can uplift these solutions to the M theory. I'm not talking about the details of it. The Lorentzian signature uplift was done by Pope, and I'm using the similar ansatz. Then I can check that all the equations of motion are satisfied. So you have the 11-dimensional embedding of this scale invariance without conformal invariance. In other words, you can start with a Euclidean ABGM theories, and then you can deform your theory such that the IR fixed point will be scale invariant, but not conformal invariant. Again, I stress that this can be only done in Euclidean signature. For today's talk, I wanted to show you one generalization of this solution. And here is essentially my last slide. And you can easily find one parameter generalization of the solution with a similar ansatz. So again, the geometry is ADS, and you have the self-dual field strength that is given by this ansatz, and you can substitute this ansatz into the equation of motion and find that there is a periodic solution given by Jacobi's SN function, and the plot is like this. So what I find fascinating here is that this is a kind of cyclic RG solution or discrete scale invariant solution. So your scalar behaves like this and then reappear from, so it goes down to minus infinity and reappear from the plus infinity. And then this point is identified with this point, and this point is identified with this point, and so on and so on. So
What happens at these divergences?
yes, I'm going to tell you after. Well, I'm going to tell you what happens later. But okay, so I'm going to tell you now. So I cannot say what happens in this particular theory because I do not know what happens in the Euclidean theory if field strength becomes.
Yeah, I'm asking this because these are allowed solutions. Though.
Yes, so it can be suspicious, but I'm not going to answer this question in a direct manner, but I'm going to show you a similar story in other examples. So discrete scale invariance is known to appear in non-relativistic systems. And the prominent example is the so-called Efimov effect. And this is given by the three-body interacting non-relativistic bosons. And the best thing about this model is that you can just solve the Schrödinger equations and find that the spectrum is discrete scale invariant. And you can numerically solve the Schrödinger equations and find out that this is what is happening. And the reason why I introduce this example is that you can also study the behavior, how this discrete scale invariance appears from our G viewport. And they computed the three body couplings of this model by studying the renormalization group of this model. And what they found is that it shows the cyclic renormalization group. But it seems likely that, again, well, we are seeing the similar plot before, that the coupling constant becomes minus infinity and reappear from the plus infinity and goes like this and like this. And you could be suspicious about this behavior if you are only working with a quantum field theory, because you say that you do not know what will happen at infinite coupling and blah blah blah. It might confine or it may and there will be singularities and you cannot continue the RG if it goes to infinity and so on and so on. Here is that this is not a good question because we know in solving Schrödinger equation, this system shows discrete scale invariance. So although you might wonder whether this coupling constant becoming infinity in this particular RG may look suspicious. In this model, you can actually see the realization of this discrete scale invariance. And I'm not sure whether this solution in the M theory is really showing the discrete scale invariance, or maybe physics would break down at this infinity. I'm not sure. I'm suggesting that this is a very interesting system to look at, and if this cyclic RG is realized, it will be great. So let me summarize my talk, and I'm going to take a why about this particular solution. So, as already mentioned by several people, like Murayama-san, and 60 birthdays in Japanese is called kanreki, and it means returning to your birth after 60 years. But as a theoretical physicist, you might wonder whether such an idea is consistent with C theorem or D theorem. But my suggestion is that, well, you can avoid it if you're working in the non-unitary theories, or if you're working in Euclidean field theories. And I said that you can use the idea of topological twist and field theories, and the idea of the selective field strength in holography are the main ingredients to realize such an idea. And everybody in this audience knows that Oguri-san is a world expert on them, and I'm sure that he can fulfill this kind of.
So I just have to break unitarities. That's all.
Or go to the Euclidean field and use the constant twist. So I wish you fruitful progress.
Okay, thank you very much for a very interesting talk with my friend. Okay, are there questions?
Yes. So what's the actual status of the situation when the theory is unitary? So there, like I know that 2 or 4 dimensions there is a proof, but and then you give some heuristic argument in general. But so what's your assessment in unitary situation?
I mean, there's no proof in 3 dimensions. Since there's no proof, just story.
Lagrange pure Maxwell theory a counterexample?
Yes and no. In 3 dimensions, you can utilize your theories the free scalar. This dualized free scalar is not conformally valid because it is symmetric. It is not doesn't have a conformal coupling to the vacuum curvature. And if you say this is a counterexample, then it is a counterexample. But
It's unitary.
and,
So I mean that whatever theorem that you can propose has to avoid this.
yeah, well, I'm assuming that they are interacting or something.
Okay.
In this.
Just a little on that. I believe all the counterexamples have infinite entropy, infinite partition function. So can you
Infinite entropy. You mean unitary theories or non-unitary theories?
The pure one cell theory has infinite entropy. You say?
I mean, in a certain sense, yes. Infinite entanglement entropy might be. Infinite partition function. Infinite partition function. Yeah, you can also say that. Yeah. So the reason, the way scaling symmetry is realized in Maxwell theory is quite a little bit non-trivial, because you say that this linear current is not gauge invariant. So what it means is that this dilatation current is not gauge invariant. Although
but dilatation charge is
dilatation charge is invariant. But this causes a little bit non-triviality, if you would like to compute partition functions and whether you can say that your partition function is really scale invariant. And people found there is some log of some scale in Maxwell theories in 3 dimensions. And maybe that's why you ask that you say that Maxwell theory in 3 dimensions has an infinite partition function.
Isn't it just a divergence from the flux sectors?
Yes.
Yeah.
Why the stations on the top? You mean the flux from what?
The electric and magnetic fluxes. Okay. They're continuous.
So maybe what you say might be.
It's still nothing from it's still an open possibility that the F theorem is true for theories with convergent partition.
It doesn't tell you anything about invariance without conformity.
I think the scale-invariant.
I don't know many examples, so I can say.
So you can consider some Lorentzian signature. Do you get some imaginary value field, or are there any sign of non-unitarity?
If you analytically continue my solutions, then there is several ways. Yes, I'm not saying that analytically continue, because I'm sticking with the twist that mixes the Euclidean rotation and eternal rotation. But if you go to the global coordinate, then there is a way to mix the rotation with the global rotation with the internal rotation. And then what I find is that there is the gauge field, the time component becomes imaginary. So it would violate.
But you have some, vaguely some candidate condensed matter system. So it has a real-time dynamics. So is it possible that actually this kind of unusual area safety somehow due to some non-unitary dynamics of condensed matter system?
Possibly, yes. Yeah, non-Hermitian quantum systems can be dual to such configurations. That is possible.